So before we get that far, let's go ahead and try to see how this collision algorithm would actually work, or this meet in the middle approach. So I'm going to go back to this example that we already know the solution to. So what's going to happen is that I'm going to cut this thing in half. What's going to happen is that I'm going to look at all of the possible combinations for those numbers 2, 3, and 4. Since there are 3 entries in that little list, what's going to happen is that I'm going to have 2 cubed, or 8, total possible ways to add up the numbers 2, 3, and 4. So what's going to happen is that I'm just going to cycle through all of those things, thinking about whether or not I'm going to choose those numbers or not. So in the interest of saving some time, I do have those computations actually calculated for us. So looking at the 2, 3, and 4, I can have the first round, which is saying, okay, don't take any of them, which would add up to a sum of 0. The next bit says, okay, take the first thing, which is going to say, okay, add up to a sum of 2. Then I'm going to say, okay, what happens if I take just the second one? What happens if I take the first 2? What happens if I take the last one? What happens if I take the first and the last? What ends up happening if I take the last 2? And then what ends up happening if I take all 3 of them? So I know it may hurt your OCD if you're looking at that little laundry list of things. There is actually a method to how I constructed all of those particular entries. And they're actually coming from creating various numbers and then writing them base 2. And what's going to happen is that I'm essentially having them reversed. So I'm going to have this particular number, which is going to be connected to a 1, you have a 2, you have a 3, you have a 4, you have a 5, a 6, and a 7, and you have the number 0. So it is kind of a sneaky way to create this little blip of whether or not I'm going to take those things, by just representing the numbers 0 through 7 in binary. Gives us kind of a really quick check for actually creating all 8 possibilities to see all of the kind of combinations emerge. So what ends up happening is that the 8 different ways the numbers 2, 3, and 4 can be added together become this little list. So you can see that I can make a 2, a 3, a 4, a 5, a 6, a 7, and a 9. So there's no way that I can make an 8 out of 2, 3, and 4, but I can make pretty much everything else under that. I also can't make a 1, but that's all right. So I'm going to do the exact same thing on the other side. I'm going to run through all of the possible combinations for the numbers 9, 11, and 14 in that same kind of funky way that I'm going to construct those. And that's up to you. This is just how I implemented it in Sage, is that I ran those numbers, I computed it in base 2. Sage actually returns it in reverse in a sense, and then I use that blip to identify whether or not I chose those numbers. So if you run that same kind of weird little game, what ends up happening is you get these possible numbers to emerge. What's going to happen is that there's going to be some overlap between these things, but I don't want the overlap between those 2 lists. Because what ends up happening is you can say, hey, they both have a 9 in them, but the 9 and the 9 don't add up to 21. So I'm not actually seeing the collision that I want to quite yet. So what I have to do is I have to pull in the actual sum. So the sum I'm hoping to see is the number 21. So what's going to happen is I'm going to take that second list and then subtract all of those numbers from 21 to see a new collection of numbers emerge. So that's exactly what that computation is going to look like. And we end up getting quite a few negative things, which is expected. But we do actually see a very nice intersection emerge. If you look at the first list, I do have the number 7. And if you look at the second list, I also have the number 7. So if you connect back to how those 7s were formulated, what's going to happen is that I have the 7 over here emerging from the 3 and the 4. So I have a 3 and a 4 added together. And over on the other side, I'm not going to pull off of the 7. I'm going to pull off of what made the 7, which is the 14. So I have a 3, a 4, and a 14, which does add up to 21, which is neat. So basically the 7 is kind of like a placeholder. Think about it as, I don't know, some number k. So what ends up happening is that I have a k, and that's where they're actually matching. But if you look overall, you're going to see that the other k was constructed by taking 21 minus this number 14, which is exactly what I wanted. So the idea is that I'm going to pull the 7 from over here, And then if you look at this blip, you have 21, which is equal to 7, which we know can be decomposed into a 3 and a 4, plus the 14, and we know how the 14 is going to be decomposed, which is actually a 14 in this one. But if the 14 came from some other stuff, we would have its decomposition reemerge. So you look at not at the intersection of just those subsets from the first little bit, but you have to take S minus whatever entry you have over there. And then you look for the intersection. So it's an extra little step that emerges. So we have the intersection with the 7, and you can see the exact little solution reemerge as the 3, the 4, and the 14. Moreover, what you can do is you can actually use this little binary representation over on the left to actually get this kind of funky X solution. So you're going to have these little blips, so the 0, the 1, and the 1, and then you're going to just merge it with the other one over there. So you're going to have the 0, and the 1, and you can see that that exactly tells you to take the 3, the 4, and the 14. So if you want to present the solution as this nice little binary vector, you easily can, or you can just represent it as those 3 little numbers added together. So let's look at the slightly more complicated one. The idea is that if I begin to increase the number of entries in my list M, the number of steps that I'm going to have to see is also going to increase just a little bit. So if I have my M, which has 8 total entries inside of it, if I wanted to do just a proper brute force thing on this, you would have to run this with 2 to the 8th, which is a lot of computations. So what ends up happening is that if I can do this collision or meet in the middle approach, I can actually drop that number as having not a 2 to the 8th, but doing a 2 to the 4th. So what ends up happening is that I have to do these 16 bits of computation and try to look for some intersections that are going to emerge. So I've done exactly that. I have the kind of nice little binary representation for all 16 ways that I can choose those first 4 numbers. So I'm printing out the binary version from going from 0 up to 15. And then I'm going to try to pad all of these things together to see what to take and what not to take. So if you go down that first little list, what you're going to do is you're going to see that there is an intersection with the number 14 and the 14 over there. What that tells me is I can actually see a solution. I'm going to have a solution of 3 and an 11, and then I got to add the other little bit over here, which is the 27. So that properly adds up to 41. So yay, I have a solution. If you wanted to view that solution with the fancy binary bit, it's going to be coming from here. So a 0, 1, 0, 1. And then the 27 was emerging from that one, which is a 0, 0, 1, 0, which is exactly saying take the 3, skip, take the 11, skip, skip, take the 27. This particular one actually does have a second solution. Let's try to change the color up. Let's do blue. If you were to look at that a little bit longer, you can actually see that there's another point of intersection, which is the number 18. There's an 18 there, and there's an 18 over here. So what ends up happening, oops, go away. What ends up happening is that I can take the 18, which is viewed as a 2 plus a 5 plus an 11, and the 18 is connected to this 23, which is achieved by just taking the plus 23, which again fires off the answer of 41. So it's a really pretty slick way to actually build up these subsets. It's still not overly elegant, but it does cut down the number of computations we have to do very dramatically, which is nice, is that it's a lot of work to do these, but the hope is that it is a hard question. If it was super easy to do, we would have no chance of actually making a crypto system out of it. So our hope is that this subset sum problem is genuinely a hard thing to look at. What we need to do next is we need to think a little bit about how we can actually change this up and make it into something that's easy for Alice or Bob to do. So before we jump too far into that one, I do have kind of the formal statement for that process that we just got done looking at. It's kind of a lot of words, but it's exactly that same procedure, is that if you give me a list M, and you give me some number S that I'm trying to find the sum for, I'm going to make these 2 little sets I's and J's, and then I'm going to compute a whole bunch of these extra little numbers. So these AI's were the things that I computed on the left-hand side, the BJ's were the numbers that I tried to compute on the right-hand side, and I go for the point in time where those 2 things do properly align. Once I know what that solution ends up being, I can actually build my sum S very easily. So this full process is then going to run in about big O of 2 to the n over 2. The idea is that I know that I have to brute force this thing on half of the list. So if I take the list, cut it in half, its length is n over 2. And there are 2 to the n over 2 subsets that I would need to test for this thing. Officially, I can add a little epsilon because there's some amount of comparing lists and finding intersections and all that kind of stuff, but that still is dwarfed in comparison to the amount of runtime that just doing the computation is going to take. So it's a pretty slow process, but it's a little bit better than the initial brute force version.